Okay, so now we're coming to something really exciting. I love the work we're doing because we can actually now say something amazing and mind-blowing about bicycles, believe it or not. All this work on angles and exterior angles in particular leads to something quite astounding. So let me tell you what I'm thinking about. So here's a bicycle. So imagine I go out on my ride, I'm like in my driveway and I go for a great big ride on a great big loop and I come back home. In fact, like this. I've got two wheels, so my back wheel will ride some loop, some path I've done in blue, and the front wheel will be a little bit in front and be riding on another loop in front. So I get two bicycle tracks, which makes sense. One for the back wheel and one for the front wheel. And I'm going to assume my loop is nice, that as I ride it, I'm always turning to the left. I'm never like switching directions, I'm always turning to the left. Because that makes sure that the front loop is outside and the back loop is on the inside. Because that then gives a well-defined area between the two loops. So, I can go in my driveway, go on a great big long journey for 7 hours, just always go on a loop that always turns slightly left and come back home. Or I can just do a short journey, goes around the block for 5 minutes, always turning left and come back home. Here is the amazing thing. No matter what loop you ride on your bicycle, on an actual bicycle, the area between these tracks is sure to be pi times r squared, where r is going to be this distance, the distance between where the two wheels touch the ground. That length is r, then this area is pi r squared. No matter what loop you ride, you will always have pi r squared for the area between the tracks. It is inescapable. You can do a really big loop, pi r squared. Do a very small loop, pi r squared. Do a really tiny loop, you're just basically kind of pivoting at one point, pi r squared. That area is a universal fact. Whoa! In fact, I want to prove this in the next video, but I just want to get us excited because this is just mind-blowing. Okay, so there's some obvious caveats to my claim. For example, I assumed I was riding a loop, always turning left and just going around once. It's possible I could do one loop that does this, or they go around once, it'll do another sub loop, then come back to the beginning. So it's done 2 full turns. In which case, the area between the tracks will start being on top of each other, but if you count that as a separate area, they'll add up to 2 pi r squareds. And if you do a loop that you ride a bicycle like this, you're going to start here and go, and then do a little twirly thing over here, and then do a third twirly thing, and then do a fourth twirly thing, and then do a fifth twirly thing, and then come back to start. Then actually you've got lots of overlapping area, but if you count the overlapping areas all separate, it'll add up to 5 pi r squareds if you did 5 turns overall. Whoa. Now this is assuming we're always riding loops where you're always turning left, or maybe always turning right when you go the other way. If you want to start changing directions, start riding left and right, then actually these tracks will start crossing over each other. So you get some area that has like blue on the bottom, pink on the top, and then other areas are the other way around, reverse orientation. Alright, so then what you have to do then, if you are going to do a loop that actually has you go left, right, does all sorts of weird things, count the area of one orientation, add up all those areas, you get little bits. Count up the areas of all the other orientations, add up all those little bits, and those two areas will differ by pi r squared, no matter what loop you ride. Now, I've got that here. I've got one orientation of area here, and the 0 of the crossing over, so I get pi r squared take away 0 is pi r squared. But here's the thing. All these amazing facts are just basic consequences in an astounding, mind-blowing way of the work we've done with angles today. So in the next video, I want to talk about all this and prove to you you cannot escape pi r squared, where r is the length of the point of contact between the two wheels on the ground. When you ride your bike tonight and go for a journey and park your bike back where it started, then you've just traversed an area between the two tracks of pi r squared. Inescapable, a universal fact. All right, love it. So let's prove this next video. See you then.